A decision problem is a question that can be answered with yes or no. P is the set of decision problems that a computer can solve quickly. Quickly means in time that grows at most like a polynomial of the input size, written as O of n to the k for some constant k. For example, checking whether a number is even can be done in O of 1 time, which is certainly a polynomial. NP, non-deterministic polynomial time, contains problems for which if someone hands you a certificate, a proof, or a guess solution, you can verify the answer in polynomial time. You may not know how to find the answer fast, but you can check it fast. NP hard means at least as hard as the hardest problems in NP. A problem H is NP hard if every problem L in NP can be transformed, rewritten, into H using only polynomial time work. H does not have to be a decision problem, it can be an optimization problem. NP complete is the overlap of NP and NP hard, a decision problem that is in NP and as hard as every other NP problem. If we could solve any NP complete problem quickly, in polynomial time, we could solve all NP problems quickly, which would mean P equals NP. Explanation: many everyday tasks belong to P because we have clear step-by-step methods that finish fast. Sorting, for example arranging a list of numbers from smallest to largest, can be done with merge-sort or quicksort in big O of n log n time. Think of repeatedly splitting a deck of cards and then putting the sorted halves back together. Shortest path in a road map, Dijkstra's algorithm finds the cheapest route from one city to all others in big O of m log n time, where m stands for roads and n stands for cities. Imagine a mail carrier who always looks at the next cheapest road. The algorithm guarantees the whole tour is the cheapest. Maximum flow, how much water can move through a network of pipes, is solved by the Edmonds-Karp algorithm in big O of v times e squared time, where v stands for vertices and e stands for edges. Picture water trying many possible routes until no more can be pushed. Each round improves the flow a little, and the total work stays polynomial. Explanation: in NP, we care about checking a solution, not finding it. Certificate: a piece of information that, together with the original question, lets us verify the answer quickly. Example: Hamiltonian cycle: the question asks, is there a tour that visits every city exactly once and returns to the start? A certificate is a list of the cities in order. To verify, we just check two things in O of n time. 1. Each city appears exactly once, and 2. Each consecutive pair of cities is connected by a road. Both checks are simple counting and lookup operations, so verification is fast even if finding the tour might be hard. A reduction is a way of turning one problem into another, using only a little polynomial amount of extra work. If we can change problem A into problem B and we know how to solve B, then we automatically know how to solve A. Cook-Levin theorem showed that the Boolean satisfiability problem S a t is NP complete by reducing every problem in NP to S a t. Think of it as a master key. Any puzzle that can be checked quickly can be rewritten as a S a t puzzle. Karp reductions are the practical tool used after Cook-Levin. For each well-known NP complete problem, Karp gave a concrete polynomial time translation from S a t or another NP complete problem. For example, to turn S a t into CLIQUE, we build a graph where a satisfying assignment corresponds to a large complete subgraph. These systematic translations let us prove many problems are NP complete. Some puzzles are famous because they capture the essence of NP completeness and appear in real life. S a t: given a logical formula with and or not, can we assign true or false to variables so the whole thing becomes true? 3. S a t: a restricted S a t where each clause has exactly 3 literals. It is still NP complete, making it a handy building block. CLIQUE: in a social network graph, does there exist a group of k people who all know each other? Vertex cover: can we pick at most k vertices, so every edge touches at least one chosen vertex? Subset sum: given a list of numbers, does some subset add up exactly to a target sum? All of these can model real situations. Scheduling meetings: clique, placing guards: vertex cover, budgeting: subset sum, or circuit design: SAT. By translating a real problem into one of these, we immediately know it is NP complete. Explanation: when we go from a yes/no question to an optimization question, the difficulty often stays or grows. Traveling salesperson problem, TSP: instead of asking, is there a route of length less than or equal to L, we ask what is the shortest possible route that visits every city. The decision version, is NP complete. The optimization version, is NP hard, because solving the optimization gives an answer to the decision version. Scheduling: assign jobs to machines to minimize the total finishing time. The decision version, can we finish by time T, is NP complete. Finding the best schedule is NP hard. These problems appear in logistics: delivery trucks, manufacturing assembly lines, and cloud computing task placement. They are hard because there are exponentially many possible orders or assignments to check. Because many important problems are NP hard, we look for ways to get good enough answers quickly. Approximation algorithms guarantee a solution within a factor of the optimal. For the metric TSP, Christofied's algorithm always produces a tour less than or equal to 1.5 times the shortest tour. Heuristics are rule of thumb methods, for example nearest neighbor for TSP, that work fast and often well in practice, though they have no worst case guarantee. Fixed parameter tractability, FPT. If a problem has a small parameter k, like the size of a vertex cover, we can design algorithms running in big O of f of k times n to the c time. For vertex cover, there is an algorithm big O of 2 to the k times n that is fast when k is tiny even if n is huge. These ideas let us cope with NP hardness in real applications. The big open question P versus NP asks if we can check a solution quickly. Can we also find it quickly? If the answer were yes, P equals NP, every puzzle we can verify fast would also have a fast solving method. Cryptography that relies on hard problems like factoring would break, and many ion planning tasks would become trivial. If the answer is no, P not equal NP, we accept that some problems are inherently hard to solve, and we must keep using approximations, heuristics, or special case algorithms. For algorithm designers, the question shapes strategy. When a problem is known to be NP complete, we stop looking for a fast, exact algorithm, unless we prove P equals NP, and focus on approximate or parameterized solutions. In the real world, routing, scheduling, security, the distinction tells us whether we can hope for perfect efficiency or must settle for good enough solutions.